high degree polynomials, the methods we've had, they often just give us approximations, numerical methods.
Close enough, maybe, for something.
Close enough, yeah, but you always have those potential rounding errors. It's never quite the exact answer. You don't get that perfect precision.
Which brings us to today. We're doing a deep dive into something pretty revolutionary here, Ezouidi's theorem.
Mm-hmm.
And this approach, it seems to fundamentally shift the landscape.
Mm-hmm.
It's a method that redefines how we can tackle these high-degree polynomials.
It really does. It lets us derive precise, exact, and this is the key, symbolic solutions, not just numbers.
Symbolic solutions. Okay, so our mission today is to unpack this. We'll look at a specific degree 18 polynomial where this theorem shines.
Exactly. We want to understand not just that it works, but how it works. And maybe contrast it a bit with those classical methods people might know.
See what makes it so different, so powerful. Should be fascinating.
It really is.
Okay, so let's set the stage. This polynomial we're focusing on today, it's quite something.
It is. I mean, just visually, it's intimidating. 19 terms.
Right, starting with x to the power at 18, then x to the 17, and so on, all the way down to a constant term at the end. We don't need to read the whole thing out.
No, definitely not. Just picture something very long and complex looking.
Because for something on that scale, degree 18, you mentioned the traditional methods, things like Newton's method.
Yeah, Newton's method is a classic example. It works by iteration, getting closer and closer.
But it's fundamentally numerical, right?
Yeah.
It generates numbers.
Exactly. It's all about approximation. So you're always managing potential errors, the rounding. You never quite land on that exact symbolic value. It's just not designed for that.
And isn't there a deeper issue too? Something about solvability itself. I'm thinking of classical algebra theorems.
You're probably thinking of Abel's theorem or Abel-Ruffini.
That's the one.
Yeah. That theorem tells us that for general polynomials of degree 5 or higher, there's no universal formula using only basic arithmetic operations and radicals, square roots, cube roots, that kind of thing.
So for many of these high degree beasts, classical algebra itself says you can't find an exact solution using those standard tools. They get labeled unsolvable in exact terms.
Pretty much, yes, in terms of radicals anyway, which leaves them in this realm where approximations seem like the only option.
Okay, so that's the backdrop. Now, Ezouidi's theorem comes along and seems to, challenge all that.
It really does. It directly confronts those limitations. It gives us a structured, a systematic process.
How does it bypass those classical constraints and the approximation issue?
Well, it avoids the need for radicals in the classical sense, and it completely sidesteps numerical approximations. The output is the exact symbolic root.
Not a better guess, but the actual mathematical expression.
Precisely, the exact thing. For polynomials that, under the old rules, might have seemed impossible to solve exactly.
Okay, I need to understand this. How does it work? What's the core idea?
So, at its heart, the theorem relies on expressing the polynomial in a specific recursive form.
Recursive, like feeding back into itself.
Kind of, yeah. Think of it as a way to break the big equation down systematically into smaller related pieces. Then we calculate a set of symbolic coefficients using this recursive structure.
Symbolic coefficients, okay. Not numbers yet.
No, symbols. That's crucial. Each coefficient is worked out purely symbolically based on the polynomial's original coefficients and the recursive relations. So no approximations are introduced right from the start.
A price from the ground up, okay. And you mentioned recursion. Is there a specific formula driving this?
There is. There's a key recursive formula. It's how we compute these symbolic coefficients. Let's call them scalar, step by step.
Okay.
The formula itself involves binomial coefficients.
Like from Pascal's triangle, combinations.
Exactly, those C and K things. They scale the terms correctly in the recursion. You use the polynomial's coefficients and previously calculated ES values to find the next ones.
So it's like an engine. It builds on itself using this formula involving those binomial coefficients to generate these exact symbolic values.
That's a good way to put it. It's a mathematical engine. And running that engine fully is what ultimately leads you straight to the exact symbolic roots of the original polynomial.
That sounds, potentially very computationally intensive for degree 18. Calculate all those S though.
You'd think so, wouldn't you? But here's where it gets really elegant, especially for the specific polynomial we're looking at.
Ah, okay. What happens when we apply this theorem, this process, to our big degree 18 example?
Something quite remarkable, actually. As you run through the recursive calculation of these symbolic scalar coefficients.
Yes. Most of them just vanish. They turn out to be zero.
Wait, really? You have this huge polynomial, you run this complex sounding recursion, and the coefficients just disappear.
Many of them do. For this specific polynomial, it turns out that 0R through S7R are all 0. And then S9R all the way up to S16 are also 0.
Wow. That's a massive simplification.
It's a huge simplification. It means that out of all those potential terms generated by the method, only two non-zero symbolic coefficients remain that are critical.
Only two. Which ones?
They're designated 0 and 17Rs. They capture all the essential information needed from that original massive polynomial.
Incredible. So that huge 19-term equation, after applying Ezouidi's theorem, effectively boils down to something involving just these two coefficients.
Exactly. The original polynomial, let's call it px, simplifies dramatically. It becomes equivalent to by 18 isolated r by 9 plus S17r equals 0.
Let me look at that. By 18, then a term with by 9, then a constant term, S17r. That looks almost familiar.
It should. If you think of y by 9, then the equation is just y2 S8y plus S17r equals 0. It's like a quadratic equation, but for x to the power of 9.
Precisely. The theorem reveals this hidden structure. It transforms the problem into something much, much simpler to solve.
Okay, so we have the values for 68r and 17r calculated symbolically from the theorem.
Yes, there are specific symbolic expressions derived through the recursion. For this example, 68r is vor-4861 times 189. And S17R is vor-8686 times 1818. Huge numbers, but exact symbolic forms.
Right. So we plug those into that simplified quadratic-like equation for by 9.
We do. So it becomes by 18 plus 48619, 189 by 9 plus 486186, 1818 equals 0.
And we can solve that for by 9 using the quadratic formula, essentially.
Basically, yes. You solve for by 9 and you get an exact symbolic expression involving 6AR and S17R, potentially with a square root.
And that gives us the value of x to the power of 9. So the final step is taking the 9th root.
That's right. You take the 9th root of the expression you found for by 9. And this is where complex numbers often come into play, especially complex exponentials, to represent all 9 possible roots correctly.
So the phonal answer, the exact symbolic root for x, emerges from this process. It's a precise mathematical expression, maybe involving complex exponentials.
Correct. It looks complex when written out naturally, involving potentially large numbers and roots. But the point is, it's exact, it's symbolic, it's derived directly through the theorem steps without any numerical guesswork.
No rounding errors, no approximation.
None whatsoever.
That's quite something. What we've just unpacked here feels genuinely remarkable. Ezouidi's theorem isn't just a small improvement.
No, it feels more fundamental.
It seems to redefine what we thought was possible for solving these really high-degree polynomials by using this systematic recursive method.
It finds these exact symbolic roots in cases where classical methods either gave up, suggesting unsolvability in radicals, or just resorted to approximations.
It feels like it bypasses that entire wall.
It finds a different path. It reveals an underlying structure like that quadratic form we saw that wasn't obvious before. It's a testament to how a new perspective, a new theoretical framework can unlock things.
Unlock things previously thought impossible, or at least intractable for exact answers. Which leads to a final thought, maybe, for you listening. If an 18th degree polynomial, something that looks incredibly daunting and was historically considered, beyond exact solution by standard radical methods, if that can yield to such a structured, precise approach,
revealing its exact symbolic roots,
then what other complex problems out there, maybe in completely different fields, problems that currently seem unsolvable or where we rely only on approximations, might just be waiting for a similar kind of breakthrough, a new framework, a different way of thinking to unlock their exact underlying truths?